So last week we saw how to use a set solver to find satisfying valuations to formulas in CNF. But we left open the problem of how to convert formulas to CNF. As we saw in the package installation problem, sometimes this is okay because the problem naturally is already converted into CNF for us. But sometimes we don't have a formula in CNF. So in this first two videos this week, we're going to look at how to convert formulas to CNF. So as a reminder, the conjunctive normal form is when the entire formula is a conjunction, so that's lots of things ANDed together, where each clause is a list of things which are ORed together, and each thing is a literal, so it's either something, an atomic formula which is negated, or it's an atomic formula by itself. This is similar to disjunctive normal form. So it's similar to conjunctive normal form, but it swaps ands and ors. So instead of having a list of things ANDed together, we have a list of things ORed together, and each of the things is itself ANDed together. So the entire formula is a disjunction, where each disjunct is an and then literals are the same. So these both have an interesting relationship with satisfiability. So in CNF, each clause is a constraint, and all the constraints must be satisfied. And we saw when looking at set solvers, this is what they try to do. They try to make sure that at least one thing in every constraint is satisfied. In DNF, or disjunctive normal form, at least one of the disjuncts must be satisfied. So we have to search through them all and look for one that's satisfied. An interesting exercise to work out for yourself, after you've seen these videos, is how would you write a set solver for formulas in DNF? And why don't we do this instead of the common set solvers which work on CNF? But how do we convert to CNF? So not every formula is already in CNF. So for instance, A and B implies B and A. So what if we want to use a set solver to determine satisfiability of this formula? So there's two ways we're going to look at to convert a formula to CNF that is the same. So there's the multiplying out the brackets technique and a more sophisticated but much more efficient technique called the Seitzen transformation. But I put in the same in quotes there, and first we need to work out what the same actually means. So the simplest way of thinking about it is that two formulas P and Q are equivalent, so written P triple equals Q, exactly when, for all valuations V, they give the same answers. And this is equivalent to both P entails Q and Q entails P being valid, or P implies Q and Q implies P being a valid formula. So this is the simplest and most direct way of saying that two formulas are equivalent. And then we can use the idea of equivalence to rewrite the formula we started with into an equivalent formula which is going to be in CNF. So the first thing to do is to take all the implications and rewrite them in terms of not and or. And so we can see why this works using this truth table here. For all valuations, the thing on the left-hand side of the equivalence is true or false exactly when the thing on the right-hand side of the equivalence is true or false. And then we can also simplify all the negations. So negating twice is the same thing as doing nothing, as you can see by this truth table, exactly when they're exactly false at the same time and they're exactly true at the same time. And we can also use De Morgan's laws to move negations inside of other connectives. So negation swaps and or. So if we have not outside an and, then we can push it under the and then we just flip the and to an or. And we can see again by this truth table this always works. And similarly for a not outside an or, we push it down and we get not and not. And again the same truth table or similar truth table works for this law. Now if we take all of these equivalences, we can rewrite any formula to an equivalent one that has no implications. All negation signs are on the atomic proposition, and we either have 0 or 1 negation signs. And this is called negation normal form. So we've got rid of all the implications and we've pushed all the negations right down to the leaves of the tree and describing the formula. So here's an example. We start with this relatively complicated formula here. A and A implies B, all implies C. And then first we convert the top level implies. Second, we convert the second implies. So this one here. So now we've got just negations and ands and ors. And then we start to push the negations through. So we push this one through here. So this and flips to an or, and we negate the a and this subformula. And then there's several things we could do here. But first we push this not through to flip this or to an and then we've got a double negation here, so we can get rid of that. So then we end up with not a or a and b, a and not b, or c. So this is now a formula which is in negation normal form, and in fact in disjunctive normal form, but it's not in conjunctive normal form. So how do we do that? Well, the way to do this is to rewrite the formula to multiply out, if you like, the ands and ors. And this is very similar to the algebraic equation where we'd have something like x times y plus z is the same as x times y plus x times z. And we can see just by this slightly larger truth table that again this works. This formula on the left is true or false exactly when the formula on the right is true or false. And then using this rewriting rule we can push all of these ors, which are higher up in the formula, down further down in the formula. And of course what we want them to be is further down below all the ands in the formula. So here's the formula we ended up with last time. And then we multiply out by pushing all the ands in, pushing all the ors under the ands, and now we get a formula in CNF. And now it's possible to do a bit more tidying up because we've got this clause here which is always going to be satisfied because it's got not a or a in it. So we can just remove this clause and then finally we can see that the formula is equivalent to this one. Now, this is a very simple and easy to understand translation to get into CNF. However, it has the severe drawback that it can lead to exponential blow-up for certain patterns of formulas. So in particular, we can see this by converting from DNF to CNF. So this formula here is already in DNF. It's disjunction, so it's lots of things all together of conjunctions. And if we follow this multiplying out the brackets route to convert it to CNF, then we get this enormous formula here. In fact, it has 27 clauses. And in general, if we have ands nested inside ors, then we're going to get this kind of exponential blow-up where we keep multiplying out and it duplicates all the subformulas over and over again. So in summary, SAT solvers take their input in CNF. Some problems are naturally in CNF, like the package installation problems, and conversion by multiplying out is a obvious way of doing this, but it can generate huge formulas. So we're going to need something better.